In this lecture, we will discuss about the smart grid protection. In continuation to our previous lecture, we will continue with the adaptive protection schemes for the microgrid system. If you see the previous lecture, we have discussed the adaptive protection scheme using the directional overcurrent relay, and in this flow diagram, the steps are involved. Here in the first step, current samples are going to be sampled at the sampling frequency of 1 kilohertz, and then the fault is going to be detected, and then the phases are going to be estimated using the DFT, that is discrete Fourier transform technique. And after that, this positive and negative sequence components of pre-fault and fault currents are going to be estimated, and after identifying this fault type, then the faulted section is going to be identified and corresponding TDS and clock settings of the overcurrent relay are going to be calculated. And this particular wing is responsible for the overcurrent relay part, and this one is responsible for the directional relay part. And both the outputs, like this is 1, if this is 1, then the final output is going to be 1. Now, to validate this particular technique, we have taken one 4 bus network. You can see here that this is our grid, and this is one renewable energy source, and this is renewable energy source 2, and these two are basically the synchronous based renewable energy source. This SBDER stands for synchronous based renewable sources. Now, we have 3 lines here, this line 1, this is line 2, and this is line 3, and this first line is protected using these 2 relays, that is R1 and R2, and the second line is protected basically using these 2 relays R3, R4, and third line is protected using this R5 and R6. And in this proposed technique, all these relays are directional overcurrent relays. Here basically in today's date in digital relaying platform, if we are using basically the directional overcurrent relay, we are not going to put any cost, because almost all the relays are multifunctional in nature. We can either use the relay as directional overcurrent relay or only overcurrent relaying, or we can also use only the directional relay or distance relay, differential relay. So, that is why this is one of the advantages of the digital relaying platform. Now, using that particular system, results are produced using the software, that is RS-CAD, and that RS-CAD software is available within this RTDS, that is a real time digital simulator. Why this platform is chosen? Because this particular platform mimics the real world. That particular uncertainties, whatever we face, saturation, transients, whatever the sort of like uneven uncertainties are present inside the actual power network, those uncertainties, those difficulties or those uncertainties can be modeled using this RTDS platform, real time digital simulator. And taking that particular platform, results system is simulated and corresponding results are produced. The first result is for grid connected mode of operation, because as already we have discussed, the microgrid may operate in either grid connected mode or it may also operate in islanded mode of operation. So, we have to check whatever the algorithm or protection algorithm we are going to develop, all the algorithms should be checked properly for grid connected mode of operation as well as for the islanded mode of operation. Coming to this first mode of operation, that is grid connected mode of operation, the results for this case, this is for the first table shows for the results for the adaptive approach, and this one is for the conventional approach. In this adaptive approach, if you could see that this fault F1, if I will go back, this is the fault situation F1, and this fault is created in line 1, and this fault F1 is going to be cleared by this R1 and R2 primary relays. And yes, of course, if this R1, R2 primary relays fail, then this R4 and R6, these are the backup relays, they are responsible to clear that particular fault. And coming to this adaptive approach for this particular fault F1, you can see here this is the peak of current before fault, this is a TDS setting, and this is the fault current table, and this is the time of clearing the fault. See, finally the point here is our check will be that CTI, this coordination time interval should be perfect, that should be within 0.3 to 0.5 second, and yes, we have attained this particular value, and this CTI is well within this 0.301 second. That is why this particular approach, adaptive approach, is successful while we are integrating these renewable sources. Maybe we have synchronous based DGs, or may we have this inverter based renewable energy sources. Now, however, if we will just come to the conventional approach, what is this conventional approach? As already we have discussed, in conventional directional overcurrent relaying principle, we assume that the clock setting and TDS or TMS of the overcurrent relay are just said to be fixed value, irrespective of the mode of operation, whether this grid is operating in grid connected mode or islanded mode, or it may be in with different types of renewable sources. So, always in conventional approach we depend on a fixed type of setting of the overcurrent relay or directional relay. So, that is why this conventional approach is producing a CTI of 0.319. I mean, yes, it is of course within this 0.3 to 0.5 second, but here our target is to be within 0.3 second only. That is what I mean, it will be just 0.30 second, but here it is exceeding this value 0.319, and in this case it is 0.360 second. So, if you see for different fault positions like F2 and F3, similar results are gathered, and it is found that finally this particular proposed adaptive approach is providing correct result in comparison to the conventional approach. Now, this is for the results for the islanded mode of operation. This islanded mode of operation means when the main grid is disconnected from the rest of the microgrid system. So, in that case also we have to check whether these relays are properly coordinated or not. That is also essential, because let us say during islanded mode of operation some of the relays are miscoordinated and they are just going to trip again. So, unnecessarily we are going to lose the healthy sections, because the islanded mode is not basically a faulty mode, right. So, that is why this relays are reactive during the faulty section or fault situation, otherwise they should not react. Maybe it is a grid connected mode or it may be a islanded mode of operation. Now, in this case also, if you could see this particular table, the left side is basically for adaptive approach and the second column is for conventional approach. Now, here the same discussion I will do, that the CTI is our target, that the coordination time interval should be equal to 0.3, right. So, here also same thing had happened, it is going to be 0.303 for this particular fault F1. And but if we come to the conventional approach, where we have not changed the clock setting or TDS of the corresponding overcurrent relay, then the corresponding CTI is exceeding, it is not exactly 0.03 second, I mean 0.3 second, rather it is 0.45 second. That means it may also miscoordinate, if we will depend on the conventional approach. Now, yes, along with the overcurrent relay performance, we also assessed the performance of the directional components. This is the directional component and here is the system, and you could see that for different types of faults, this AG fault, ABC fault and corresponding directional element is here evaluated, and if you could see this is F1 is basically this if we consider this relay, I mean this M1, M2, M3 different modes of operations. This M1 stands for grid connected mode, M2 is islanded mode of operation, M3 is disconnection of DERs. Why this M3 stands for, like in microgrid system it may happens that maybe we are going to lose some kind of renewable energy sources. We have many number of renewable energy sources which are connected to their respective buses, I mean particular locations. Now, let us say due to some fault or due to some maintenance problem, 1 or 2 DERs are going to be out of order, I mean it is out of service. So, in that case also our relays should be intact and they should coordinate to each other properly, because disconnection of DERs basically it is not a faulty case. Now, here for this M1, that is the grid connected mode, M2 and M3, for all the cases this particular directional unit is operating fine. If it is plus, this plus side designs, I mean it describes the fault is basically behind the relay. If it is -1, then this fault is in front of the relay. So, these are different situations we have created, and you can also try by yourself by taking the system and taking the particular data, and then corresponding results can be obtained. And this is the particular compass plot for these phases to make it more clear that I will just explain one here. The programs like for AZ fault type, and the fault position is F1 during the grid connected mode. The first figure is for the fault at F1 position and for the grid connected mode of operation of the microgrid system. Now, here this is the position of I1 pre, the fault current, the positive sequence pre fault current which is flowing through the relay, that is the position, and this is your I1F. If the fault is located at F1 position, the corresponding positive sequence current, this I1F, and this is my superimposed fault current. This is a resultant of this particular between this I1 pre and I1F, and so it lies here. And as we are taking the angle between the superimposed current and I1 pre, so that is why this angle is basically, if you could see here, angle between this and this is going to be what? Because it is leading, this delta I1F is leading to delta I1 pre. As a result, the angle is going to be positive. That is what is written here, plus 2.48 radian. All these angles are basically in radian. Now, if we will come to this one, the second one, the second figure, that is for the fault position F2 during the grid connected mode of operation of the microgrid system. And here it is just the opposite case, because we are taking for the particular grid mode of operation. That is why this I1 pre is going to be constant. If this basically it is a flow of power, the power flow direction, that is why this phasor position of I1 pre is going to be constant, whether it is basically for F1 position or F2 position. That is why here this I1 pre position is constant as the previous case. Now, here for this fault position, this is the fault current phasor, and this is a corresponding resultant between this I1 pre and I1F, that is a superimposed fault current. Now, this if you could see that in this case this delta I1F is basically lagging to this I1 pre, and that is why this angle is going to be negative, minus 2.28 radian. So, this is a very good assessment using this MATLAB compass plot. You can see easily that how these phasors are lying within this polar plot. Now, we have done a very good laboratory arrangement inside this Department of Electrical Engineering IIT Roorkee using this RTDS. As I said from the beginning that we have used this real time digital simulator platform for the simulation of different types of microgrid system, and this is a very advantageous case that in RTDS there is availability of solar system, wind system, fuel cell, batteries. So, all kind of renewable sources are basically available in this RTDS software, and the analog signal, and there are different types of analog cards. So, using this analog output card, we have taken the 3-phase currents to the D space. This is the D space 1 and 04 board, and here the algorithm is basically written inside, it is burned inside this processor of the D space, and after getting this 3-phase current signals, this algorithm is going to be executed, and after that the trip signal will be sent to the corresponding circuit breaker to take the the shutdown or trip the basically the DGs or renewable sources. So, this is what is known as hardware in the loop test bed to test different type of relaying algorithms. This is one of the few we have simulated many hardware results and we have collected, and this is one for example that this is for the fault F2 position during islanded mode of operation, and the first figure is for the conventional approach and the second one is for the adaptive approach, the technique what we have developed. Now, in this conventional approach, if you could see here that this time trip signal is quite large, it is almost 1.19 second. However, in this particular proposed approach, this time trip signal is generated within 0.98 second. That is one of the advantage, it takes less time. And here also if you can see the second one, in this case the same thing, I mean this proposed approach, the trip signal here, the trip signal is 1.19 second. However, in this proposed approach it takes 0.412 second. So that is why, I mean in hardware platform also we have validated the proposed technique, and it is quite possible because as we are using this sequence component based technique, and that switch is based on current information. So, it is a very good platform to implement in real time as well, because whatever the technique we are going to develop, that should be implemented in field, otherwise it has no meaning. It should be feasible in the practical field. So, that is what this test hardware results tell. Because if simulation is not sufficient, we have to test whether this particular algorithm is going to be implemented in real time or not. So, that is very important. And if you could design some very fundamental basic techniques based on the information of current, voltage, some parameters, that is very good, because it will be very easy to implement in our digital relaying platform. Now, I will come to another very important concept of this particular adaptive directional overcurrent relaying principle, that is based on the superimposed adaptive sequence current based second method. And if I will just describe very quickly, because already we have discussed many components that what we did in the previous technique, and what is the basic difference between the previous technique and this technique, I will just highlight. In this case more or less we are going to also again depend on the sequence components of the current only. These two techniques are based on only the current information, not the voltage information. Here we are not using any voltage information, we are just using the current information. In this case we are also dependent on the positive sequence pre-fault current and the negative sequence pre-fault current. And again we are also calculating this positive sequence fault current and the negative sequence fault current, and also we are calculating the superimposed positive sequence fault component and the superimposed negative sequence fault component. Here one addition we did here, that in this particular technique two distinct difference I will just tell. The first one we did here, we have designed one impact factor. Why this impact factor comes to the picture? Because I just want to highlight here that in our microgrid system we are using different types of renewable sources, right. So, DERs. Now, what happens if any fault will be incepted, the synchronous based DG will supply more than 5 per unit of the rated current. However, at the same time the inverter based renewables will supply the fault current in the range of 2 per unit, within this 2 per unit of the rated current. So, there is a huge difference. I mean this inverter based DGs clamps the fault current magnitude, whereas the synchronous based DG does not. So, there is a mismatch between the fault current label. That is why this is the main reason that why this overcurrent relays miscoordinate. So, to bring the fault current label to proper order, I mean as I said in the inverter based DG, the fault current is clamped to 2 per unit. If we could bring to the right level, we can modify or we can just manipulate the fault current again to the right position, then yes, of course we can always avoid this miscoordination between the overcurrent relays. We have tried to overcome this particular problem using the this impact factor concept. Now, this is one of the impact factor which is used for this inverter based DG. What is that? Delta I1F plus delta I1 free with respect to the superimposed fault current, that is delta I1F. That means yes, of course in this case the numerator is greater than the denominator, and it will just multiply with the corresponding fault current here. After getting this impact factor, the finally modified fault current, see this is important, this IF is a modified fault current which is addition of this delta I1F, delta I2F, this positive sequence fault current and negative sequence fault current summation multiplied by this impact factor. So, that will be my corresponding modified fault current, right. So, that IF will provide me proper coordination between the primary and backup overcurrent relays. Now, for synchronous base disease, we have just reduced the impact factor. So, here in this case this numerator is less than the denominator, because we want to reduce the fault current to proper level. Of course, in sometimes we do in other way around also. So, and that is the case, yes, of course, in case of synchronous base DG, sometimes it is also not needed the this impact factor, because it is already more than the 2 per 3 per unit the fault current of the rated current, right. So, in this case it is not necessary, but however, in case of inverter based DGs, this impact factor multiplication is must. Now, same formula we have just the concept we have developed here, this TDS. Here we have taken the revised TDS. The TDS will change as the mode of operation of the microgrid system is going to be changed, and that is what this FMR and FMC, and this is the corresponding old TDS, and this one is, this TDS is the new TDS. Now, after that we again, this particular system has been taken, this F1, F2 is basically the fault positions, and this is the directional relay, and this is the DR, the distributed energy source, and this is the grid, and this is the corresponding sequence diagram. If any fault occurs at the F1 side or F2 side, or there is no fault, so this particular figure is basically used to calculate the corresponding fault current or pre-fault current at the relay location at this point. At this point we have to basically calculate this I1 pre, and then I2 pre, then I1F and I2F, and of course these two fault currents we have to calculate for F1 position as well as F2 position. So, these are basically the analysis part, and here the corresponding sequence diagram has been described. This is the corresponding sequence diagram of this particular system. And if you could say, after deriving, it is observed that this in this particular phasor diagram there are two phasor diagrams A and B, and here you could see this already we have discussed the phasor diagram for the positive sequence based directional element. Here I am emphasizing for the directional element for the negative sequence component, and this is the position of I2 pre if it is so, and then the corresponding this particular fault current, that is I2F. This is with the corresponding negative sequence fault current position, and their resultant, this is the difference, and that difference is nothing our superimposed current, this delta I2F. If you just see, I have written here this delta I2F1 is nothing the fault current, negative sequence fault current for F1 position minus the negative sequence pre-fault current. Similarly, after getting this superimposed negative sequence fault current, we have to take the angle between these two, that is the negative sequence superimposed current and the negative sequence pre-fault current. This angle is basically our requirement, and similarly the next superimposed fault current is basically delta I2F2, that is I2F2 minus I2 pre. So, this is all these are basically the phasor subtraction. Remember, these are all phasors. They have it all the phasors quantities have like magnitude as well as the angle. Now, after getting this superimposed component of the negative sequence for the F2 position of the fault, we have to find the angle. This delta F phi F2 is nothing angle of this particular phasor and angle of this particular phasor. The difference of these two is basically the angle difference. After getting this angle, what conclusion we will get, how to determine the fault current, fault direction, whether it is in front of the relay or behind the relay. Now, if you could see in this case, in the first figure A, this delta I2F1 is leading to my I2 pre, right. So, that is why as if like this delta I2F1 is leading means, yes, of course, we always in the phasor domain we move in anti-clockwise direction. So, this is leading to this delta I2 pre, as a result this angle is going to be positive. Now, here in this case, if you could see the same analysis we did here, the angle is basically this delta I2F is lagging to this I2 pre, and that is why this angle is going to be negative and this angle is going to be positive. So, this is a very important concept, that if here is my bus and here is my directional relay location, and this is my F1 position and this is my F2 position. For this F1 position, this phi is going to be positive, and for this F2 position this y is going to be negative. So, this is the rule base for the directional relay. Now, we have validated this particular technique, I mean the overcurrent relay, this impact factor concept based overcurrent relay, and this negative, here we have added both positive and negative sequence based directional elements. So, together the if suppose somehow this let us say for positive sequence based directional element basically fails for high impedance faults, high resistance fault case. However, in that case this negative sequence directional element will help. So, that is why the two directional elements are added together in case of directional unit. And together to validate these techniques, we have also taken one system, and here the flow chart for this particular technique. This side is my overcurrent relay part and this is the directional unit part. And you could see here that the main important aspect of this proposed technique, basically this for this particular proposed technique, is it is highly dependent only the current information, not the voltage information. That means we can save, I mean cost wise we are in benefit. And second point, here in the directional unit we have taken positive sequence directional element and also the negative sequence directional element. Any one of fails, the other one will help us to provide the direction. And as far as the overcurrent relay is concerned, here we have used one impact factor concept, and that impact factor will help you to boost the current, fault current magnitude in case of inverter based DG, and it may also reduce or to bring to proper level in case of synchronous based DG, so that the primary and backup overcurrent relays are not going to be miscoordinated. This is the system we have simulated using this RTDS system, that is real time digital simulator IEEE 34 bus system. In this system we have taken this PV, this DFIG and synchronous based DG, right, and this is our grid and different fault locations you can see here, F1, F2, F3, different locations we did, and these are the sum of results. And this is my, as I said, for the overcurrent relay our main aim is basically to check whether the CTI is within proper range or not. Here we have maintained within 0.3 to 0.5 second, and you could see this is proper, it is not exceeding 0.5 second. And coming to the directional part also, for different fault positions the mode of operation M1, M2, M3 and M4 also we have taken here. Here the +1 means the fault is back side of the relay and -1 means the fault is in front of the relay. So, that means all the what are the techniques we are just proposing here, we can always test it using the hardware setup also. These are the results for the positive sequence based directional unit, and you can see here if the fault is behind the relay this will be plus, and if it is in front of the relay this will be -1. Now, this is the hardware setup. Already we have discussed this setup, and this particular technique is also implemented using this hardware in the loop system, and this is the corresponding sum test results. So, the conclusion here is if you could see here that the whole the results we have discussed, and I have started like smart grid protection schemes. If you could see, the final conclusion is that we need adaptive protection schemes now, because now this microgrid system or the smart grid, I can tell this microgrid system is part of the smart grid system. This smart grid system needs absolutely without any doubt the all the ways the adaptive protection schemes. The conventional fixed mode of operation of the any relays, not only this overcurrent relay or directional relay, any relay, maybe differential relay, we are going to also use this relay. So, the fixed mode of operation of the conventional technique is not going to be operating nature, it will not operate properly as far as the smart grid protection scheme is concerned, because these renewable sources are like solar and wind are very fluctuating in nature. That is the first point. And second point is the current contribution during the fault position from different types of DERs also different. And again, this earlier the distribution network was very radial in nature. Now due to the integration of renewable sources, this radiality is not anymore. So, this power flow or fault direction may be reverse in nature, it may be bidirectional in nature. So, keeping all this in mind, it is very essential that this conventional fixed mode of operation of the, I mean this all the relaying schemes are not going to work fine. So, we have to propose definitely the adaptive protection schemes. In that sense, from this IIT Roorkee side, our team like protection group, we are trying to have some developed protection schemes for the smart grid system, and we have also this hardware in loop test bed to test all kind of proposed algorithms. I mean not necessarily this protection, also other control strategies as far as the smart grid is concerned. If you could see that now in this smart grid environment, this fixed mode of operation of the protection schemes are not going to work out, because every time this renewable sources we are going to implement, like those are fluctuating in nature, and moreover this fault current contributed by different renewable energy sources are different. I mean as far as the magnitude is concerned, different. If you could see, the inverter based DGs basically clamps the fault current to 2 per unit of the rated current, and also the synchronous based DGs basically provide 5 per unit of the rated current, I mean the fault current magnitude. So, in that sense this is also one of the concern. And one more concern, basically if you could see that in distributed energy sources or smart grid environment, if any fault occurs, the fault direction reversed, I mean the bidirectional fault current takes place. I mean the power flow is now bidirectional instead of unidirectional. Earlier the distribution network was radial in nature, but now due to the integration of these renewable sources, this radiality is not anymore. So, that is why these are the different concerns, and we are also proposing the demand side management, so different new concepts as far as the smart grid is concerned. So, that is why this fixed mode of operation of the protection scheme is not anymore, I mean going to work. So, that is why this adaptive protection schemes to be sought. Thank you so much.